Alright, welcome back, Davidson Physics students. This time we're going to be looking at a couple of sample problems similar to what we did before, but a little bit more involved. The first one we're going to look at is we're going to have a cat jumping off a building that is 3 meters tall. So here is our little cat with some legs, give it a tail, and some whiskers, no eyes. That's why the cat fell off the building. We're going to say that this is 3 meters up here, and rather than looking at how fast the cat is going right before it hits the ground, let's look at how fast it is going when it is a meter off the ground, so 2/3 of the way down. We start out with our conservation of energy equation, so our initial energy is equal to our final energy. Up here at the top, the cat has some gravitational energy. As it falls, it loses some of that gravitational energy as it becomes kinetic energy. But when it's a meter off the ground, we would say that it still has some gravitational energy left. So we need to account for that over here on the final side of our energy conservation equation. Now, if I have gravitational here and here, I should do something to distinguish between the two. So I'm going to call this initial gravitational energy, and then that guy will be my final gravitational energy. Once we have our conservation equation set up specific to this situation, then we can go ahead and start plugging in our equations for each of these types of energy. I'm going to have mg, I'm going to call this y0 for my initial height. Over here I'm going to have 1/2 mv squared plus mg, and then my final height. Masses do cancel out, which is why I didn't give it to you. You'll notice in any of your homework problems when you don't have mass and you are worried about not knowing that, it will pretty much always cancel out. So that's kind of a little clue that you should look for that to happen. Alright, now I can go ahead and start plugging in my numbers. I'm going to have 9.8 times 2 equals 1/2 v squared plus 9.8 times my final height is 1, so this is just 9.8. From this point we have a bit of algebra. Works out to be the square root of 39.2, which is approximately equal to 6.26 meters per second is how fast the cat is going at that height. So here we had to deal with not all of our energy going into another type, but there was some left over still. But as I mentioned earlier in the previous video, we can choose whatever height we want to be zero gravitational energy. I didn't say it explicitly, but implicit in this information is saying that ground level is 0. But we don't have to make that 0. I can call this level here 0, which is going to make this, let me erase this real quick, it's going to make this a height of 2, and in fact it's going to make this -1. Alright, now if I shift my perspective like that, then when I have my initial equals final set up, I start out with gravitational energy and I end up with just kinetic energy. No gravitational left if I'm calling this a height of 0. So then I can just have mg y0 equals 1/2 mv squared. 9.8 times 2 now equals 1/2 v squared, and you solve that and guess what? You get exactly the same thing. So once again, choose whatever height is 0 according to the situation to make it most convenient. Now what about this negative thing? What if I'd plugged in a negative height if I was solving for how fast the cat was going when it hit the ground? Well, my equation would still work out. Even if I had a negative height, I would have a negative gravitational energy, and that's okay. We can have negative potential energy. What we can't have is negative kinetic energy, because if I think about 1/2 mv squared, none of these quantities can be negative. Well, v can be negative, but I end up squaring it. So I always have positive kinetic energy. So we can have positive and negative potential energy. But when we say that it's negative, that has nothing to do with with direction like we saw with forces and velocity. Energy is a scalar quantity. So we can have negative energy, but it's not saying it's going another direction. It's just the magnitude can be negative. So that's kind of an important little thing to understand. Alright, let's look at one more sample problem. This time we're going to have a slingshot firing a rock. Got a problem with my slingshot. Well, whatever. Firing a rock into the air. Okay, and let's say this guy is going to follow some parabolic trajectory. Let's say the initial angle, even though it doesn't look like it, let's say it's 30 degrees. We'll give you the mass of the rock, 0.25 kilograms, the spring constant for the slingshot, the rubber bands or surgical tubes or whatever your slingshot is made of. Let's say that that is 200 newtons per meter. And let's say that we pulled our slingshot back 15 centimeters or 0.15 meters. And I want to know how high this rock is going to go. So we start out with conservation of energy. The energy we start with has to equal the energy we end with. Can't be created or destroyed. We start with elastic energy. If I call this a height of 0 meters, so we assume we don't have any gravitational energy. Start out with just elastic. I end up here. This is my final situation. I've got gravitational because it went up higher, and the rock is moving following that trajectory, so we have some kinetic energy. So I want to solve for the height. If I plug in my equations, I've got 1/2 kx squared. As I mentioned earlier, usually we get lazy and leave off the delta x there. And then we've got mgy. That's a pretty ugly m. That y is what I'm going to be solving for. And 1/2 mv squared. Can't really cancel out anything here because there's no mass in this term here. I know both of these things, but I don't know my velocity, which is going to make it impossible to solve for that maximum height. But we can use some of our knowledge of kinematics and projectile motion to figure out the velocity at that height. And what we want to do is we can actually use conservation of energy again to figure out the velocity when this thing just left the slingshot. So I'm going to jump up over here and I'm going to say the initial energy equals the final energy, but now I'm just saying from the time I pulled it back and to the time that it just left the slingshot. So when it was pulled back, I had elastic energy. When it just left the slingshot, I'm going to ignore the little change in height here. We like to do that in physics, ignore things when we feel like it. So here all of my elastic becomes kinetic energy. So this is going to allow me to find the initial velocity, the launch velocity of our rock. So we've got 1/2 kx squared and 1/2 mv squared. If we plug in our numbers here, we're going to have 1/2 times 200 times 0.15 squared equals 1/2 times 0.25, just squeezing it in here, times v squared. This side of the equation works out to be 2.25 joules of energy equals where did I go with this? Yeah, okay. 1/2 0.25 v squared. Solve that guy for v, and you end up with 4.2426, and you should keep as many digits as you reasonably can. When I did these calculations, I did it in my calculator and just use all the digits that the calculator would store. Now I'm also going to call this the initial velocity, just to remind myself that it's not this velocity here. I haven't found that quite yet. This is just the launch velocity. So if I think back to my information about projectiles, if I know the launch velocity here, I could technically use that information and use a kinematic equation to figure out how high it goes. But since we're doing energy, we're going to do something a little bit different. At the top of the trajectory here, I know that I don't have any vertical velocity. I just have an x component to my velocity. I also know that the horizontal velocity is constant along the motion of a projectile. So if I find the x component of the initial velocity, I know the total velocity here because that's all the velocity we have left. So the x component, if we remember our little triangles here, I want the horizontal part. This is my initial velocity. There's my 30-degree angle. So I'm going to use cosine. So V naught cosine theta. My initial velocity is this 4.2426 guy times cosine of 30, and that works out to be a velocity of 3.674 meters per second. That's the velocity that I can plug in here because that is my total velocity at the top of the trajectory there. Now I can go ahead and plug in my other numbers and solve for what I was looking for, the height. I already know the elastic energy I started with. That's what I solved for over here. So I started with 2.25 joules. I don't need to write the units, but you can. Here my mass, 0.25 times 9.8 times y plus 1/2 times 0.25 times, I'm going to get a little crooked here, sorry, 3.674 squared. Anyway, you do the algebra from this point. Turns out you get a height of 0.23 meters. So not the best slingshot launch in the world, but some good physics going on. Alright, I will see you next time. Same physics channel, same physics time. See ya.